Yeah.
So
Hello.
the three of us have been co-authors before, so that's why
I know.
I just pointed her to it long back now, right? So I don't need to say much about Katharine Hayhoe. She's a climate scientist and a climate communicator par excellence. You have seen our, I don't want to embarrass you, so you have seen the Time 100, UN Champion of Earth, etc. And right now, her role, I think, in addition to Texas Tech, right? So she's still there at Texas Tech as a distinguished professor. But in addition to that, she is the chief scientist of the Nature Conservancy. And so are we set, more or less?
We might need help with setting up Katharine's laptop. So.
Oh yes, please. Okay, just give us just 30 seconds more. So I'll leave this to Katharine, hand it over to her. There's a need to set up the laptop. She's okay with recording. Actually, our dean asked us to record. So if it's okay with you, we'll record. If any of you object, we'll not record. Is it okay with all of you to record? And everybody online, I'm hoping it's okay with all of you. If not, please let us know. And I'll hand it over to Katharine to set up the laptop. Thank you, sir.
Sure. Hello, good, thank you. What do we need to do to set up?
Just
Plug in? Oh, well, that's easy.
Yeah.
I can see it.
Set up, please. Set up the recording.
Oh, yes.
So it's recording on the Teams call?
And that should be fine. Oh, but you need me to share my screen.
Yeah, if she should.
Yes. So what I can do is I can join the Teams call and then share my screen.
Yeah.
Right. I will do that. Okay. So that's my, okay. So just a second here, then let me get the, just a minute. Was it? I'm not sure if my text message or my email. So let me just check. Hang on a second.
It should be.
During the round table. We'll do the introductions after.
Just, no, I actually have it in my text message.
At 4, so I need to leave at
She's also going to leave at 4, almost sharp. She has another.
Link.
But I need to be across.
You need to, yeah, that's all right.
So
Yeah,
I need to leave at like 3:30.
That's okay.
Yeah. Okay.
Just so
Like it's working. There. See, Teams is always very confusing because I have 5 different Teams accounts.
Oh, wow.
And Teams doesn't let you switch between Teams accounts. And so I sometimes end up sitting in waiting rooms for 5 or 10 minutes. And I'm like trying to find an email address to send somebody to say, I'm here, but and they're like, oh, what's the wrong? So I have one with the university. I have one with the government because I'm a national climate assessment author. I have one with Texas Tech University. And then I have another one with another company that I serve on an advisory panel with. And then I have a 5th one. I don't even know what that one is.
Before you click on that,
yes.
do you have audio that you're going to be playing?
No, I don't.
Okay. Well, you should
I
just
can
go to
turn on my
room audio.
camera. Okay, room audio. There we go.
It's been 216.
Search for room 216. Okay. I'm unable to find any rooms.
Yeah, you just got to give it a second.
Okay.
Are you connected to the?
I'm on the Rome EDU.
Really?
Yeah.
We're getting government teams count.
Okay.
Well, you're on, right?
Yeah.
So we could just use her audio probably.
Like in the teams
Yeah.
together and like.
Disregard that.
Yeah, I think that might be easier.
So just do
Okay.
computer audio.
Yes.
Computer audio. Okay, there we go. I can join now.
With my external number.
Okay.
So it was remote.
So you have recording turned on, right, Ayushi?
Yes.
And one of you, I think Ashish, or one of you can help later.
Yeah, you want to keep your audio
Audio off.
muted. You don't want to.
Mic. There we go.
Oh, wow. That's rough.
Ooh.
Can you hear us?
Yes. That is a little scary. Maybe we could remove mute that.
Have yours muted.
Oh, no.
Is there somebody else logged in?
Robin,
On Teams.
can you hear
Yes,
us? Okay.
yes,
Great.
I can hear you fine.
Good. Can you hear me?
I can hear you great. I just can't see your slides yet.
Okay, but do you see a white screen?
I do.
Okay. then I think we should be good to go.
Oh.
Yeah, it's just a white screen.
So should you be muting?
Yep, everything looks great.
What if it's this that's?
Yeah.
Do we need to
I
mute
did
it?
mute it.
We-
There we go.
Okay.
Yeah, it
That
should be
might-
good now.
Okay,
All right, great.
good. All right, and I wonder if, there.
Sure thing.
I put myself down a little bit because otherwise everybody's looking at the bottom of your chin when you set the laptop in front of you. So if you're wondering why I'm sitting so low, so that they can see my face. All right, so I actually wanted to start because we don't have enough time to go through everybody, which would be really fun. But I would just love to ask you some questions. And so the way that it's easy to do it is this. So if you have your phone with you, or you can do it on your computer too, you just go to polev.com/Katharine, or you just take a picture of that. And you can do this online too. So if you're online, you can do this. It doesn't matter. You can do it online or in person. And then when you go there, I wanted to ask you this. In one word, what do you work on? So if you didn't get it yet, the QR code is still there up in the top. And the link is there too. The link is polev.com/Katharine. So I'm expected water. Oh, good. Okay. We got more than water. Policy, climatology, climate. You can see why it has to be one word, right? Because it's a wordle. Climate and water is writing to the top. Plastics. Oh, psychology. Who's psychology? Oh, great. Geospatial. Oh, justice. That's a good one. Who does justice? Maybe somebody online, I guess. Oh, no, down there.
Justice technically.
Yeah, I assumed, yeah. Yeah. Climate is kind of the cover-all, and then
Exactly.
adding an extra sensors, governance, air. Excellent. Okay. We're just doing something fun. You can just, if you have your phone with you, you can just take a picture of the QR code up there, and then it'll just show up on your phone right there. Okay. Now, I wanted to ask you another question, which is, why do you do what you do? Now, this one's a bit different because, and these are anonymous, I don't know who's answering what, and if I ask, you don't have to confess if you don't want to. But this one, you can say whatever you want, that can be as long as you want, but you can upvote other people's answers. So go ahead and answer, but then if you see other answers that you agree with, I want you to upvote them. Why do you do what you do? You could do a lot of different things. As a climate scientist, people often say, well, you're in it for the money. And I'm like, no, if I want to make money, there's a lot of other things I would be doing. So why do you do what you do? That's a really good one. I want my children to have a better future.
Still one word?
No, you can use more than one word this time. Novel solutions to important problems. That's a good one. To have an impact. Public service. Yeah. Love of water and people. Oh, I love that. Because it's hard. That is not a bad reason. Because it feels good to do something. So you can see them popping up, but on your phone or your computer, you can see the full list. And go ahead and give thumbs up to the ones that you agree with, even if you didn't write them. Because I'm just curious what's going to rise to the top. Why do we do what we do? I've never asked a group of us this question before, so I don't know what the answer will be. So it looks like to help plan for the future is rising up, to understand climate science and change and solutions. I like that because, 20 years ago, it might have just been to understand climate science, right? But now we've got solutions there. Solutions to important problems, yep. I want my children to have a better future. Yes, that's a huge one, isn't it? So I was just at Climate Week in New York last week, and one of the sessions I went to was by a marketing group called Potential Energy, and they just finished surveying all the G20 countries around the world. So that's about 70% of the world's population. And they were surveying them on climate change to see how concerned they were, and then also to see what messages resonated the most. And it turned out that the #1 message that resonated the most all around the world, and this will be no surprise to you, about why people cared about climate change and why people wanted to fight for climate solutions, was love of their children. That was it. I don't know how much money they spent. I think they probably spent at least a year doing that, but that's the result they got. And this was free and it took us 1 minute. But it's got how many? 16 votes now. So that really is sort of like a unifying human perspective, isn't it? It's not necessarily even your own children, because it might be nieces and nephews. It might just be knowing that children are the next generation for all of us, and that's how we continue into the future. That's how our ideas and our work continue, is when other people take it up and take that into the future. So I love the fact that we've got children here, we've got solutions in here, we've got love of water and people, love, of course, being a really important word. It was interesting because at the end of this whole presentation, 90 slides, they're like, well, it all boils down to love. And I'm like, I think I've heard that before. In songs and religious texts, in psychology, right? And so it's really interesting because, 20 years ago in a group of climate scientists and hydrologists, we wouldn't be talking about those words, would we? And yet today, here we are. So when I said that I was coming to Boston, I asked Arup, do you want me to give a talk or anything? He said yes. He did something very unusual. And in years and years of visiting different groups and giving talks, I've never had anybody say, just get up and talk about whatever you want. We're not giving you a title. Never had that before. This is the first time, and I love it. I think it shows great trust. And we have, we've authored a number of papers together, and we've worked together for a long time. And so I just thought that was really great. He said, just talk about whatever is at the top of your mind. I was like, why not? So first of all, I wanted to see sort of what's at the top of your mind in terms of why you do what you do. And then what I want to do is I just want to leave this open as I talk. When it comes to climate change, what's on your mind that you'd like to talk about today? So as I'm going, I have some thoughts to share. If anything occurs to you now, or in 5 minutes, or in 10 minutes, go ahead and put it up here. And you can go and check and see what other people put up and give a thumbs up to the ones that you agree with. So in terms of what's on my mind, I felt like what's on my mind is the product of all the different turns that my life has taken over the last, I guess it's been about 30 years. Well, no, even more. Really, my whole life. So, which is a lot more than 30 years. So I actually wanted to start with the, way back at the beginning, and sort of show you how my life experiences have informed what I'm thinking about today and what's top of mind, and how that changes. That's a very good question to have at the top. We'll get to that one. So starting off, and I used a blank slide because that's what we're starting with. So we're just starting with a blank slide. I figured I would start way back at the beginning, which is, why did I become a scientist? So this is me, and this is my 7th birthday party. And if you will notice in the corner, there is an object. I don't know if you can tell what that object is. Right there, it is a telescope. That telescope went with us on every family vacation. In fact, it determined our family vacation. Our family vacations were predicated on where there would be a comet or an eclipse or another astronomical event, because my dad was a science teacher. And so that meant that I grew up with the idea that science is the coolest and most interesting thing you could possibly study, and why would anybody do anything else? Don't you want to figure out how the world works? Of course. So it's no surprise that by the time I made it to university, I was studying astronomy and physics, and if you look at my t-shirt there, that is, I will confess, the evolution of galaxies on my t-shirt. So why I became a scientist was pretty much a product of my upbringing. I'm not sure I had a choice, really, but I never regretted that at all. And my first few publications are actually in the field of astronomy. I originally studied variable stars as an undergraduate, and then I did sort of a pre-doc as opposed to a postdoc, where we looked at galaxy clustering around quasars. And I really, really enjoyed it. So some of you said that you do what you do because it's hard. I love doing this. I mean, what is harder than figuring out what is happening at the far outer reaches of the universe using nothing more than the tools we have on this pretty insignificant planet? That's hard, and it's fun. But while I was finishing my undergraduate degree, and while I was already looking around for and applying to graduate schools to continue observational astronomy, I had to take a breadth requirement. I hadn't finished my breadth requirements. And I looked around, and there was this brand new class over in the geography department on climate change, and it was being taught by this guy. This is Danny Harvey. Now, little did I know, but Danny Harvey had just moved to the University of Toronto. This is a more recent picture. and this was many years ago, we're talking the 90s now, he had just moved to Toronto from NCAR, where he had been working at NCAR with Steve Schneider. Now, if any of you know Steve Schneider, we lost him a number of years ago, but he was one of the most dynamic and compelling climate scientists of our era. He inspired many of us in our work and still continues to inspire me today. And he inspired Danny, and Danny inspired me. It took me a while to connect those dots. So I was in this class on climate change, and I was completely surprised to find out 4 things that I never knew. And the first was, I didn't realize that climate change is not just an environmental issue. I had always thought that climate change was an environmental issue that environmentalists worry about and environmentalists work on, and the rest of us wish them well and support them and watch their documentaries. But climate change is not just an environmental issue. It affects people, food, water, physical health, mental health. It affects every aspect of the natural environment. It affects infrastructure, the economy, supply chains. It affects everything. Even national security and geopolitics. The second thing I didn't realize, and bear in mind that this was back in the 90s, I didn't realize that climate change was already a present issue. I thought it was still a future issue. And believe me, there's still people today who think it's still a future issue. But that class made it really clear it isn't. It's happening now. It's not just in the future. And then I didn't realize that climate change affects all of us, but it doesn't affect us equally. So populations who are already marginalized, who are already vulnerable, who don't have a safe place to live or clean water to drink, they're the ones who are most impacted. And I don't know if you could see that picture. You probably got distracted by the galaxies on my shirt. Behind me, that wasn't Canada, where I'm from. That was Colombia, where I grew up. So I grew up in a country where I had friends who didn't have running water, who didn't have enough food to eat, who, the floor of the home is mud. And, when you put out your garbage, it's pretty much gone before the collector comes because it's so valuable to people to use to make things out of. So when I learned how unfair climate change is, and I learned what disasters look like, I knew. I had already lived through landslides and earthquakes and hurricanes, and I knew what that looked like if the only place you can build your home is on the side of a mountain, because that's the only place that people don't own property. And then the last thing I learned was that climate science was the same physics I'd already been learning. I don't know what I thought it was, but I didn't think it was that, and it is, right? It's exact physics. It's nonlinear fluid dynamics. It's radiative heat transfer. It's a lot of computational work. And even the orbital dynamics, which I'd learned about in astronomy, explain the ice ages. So that was when my life took its first turn. And that's why what's top of mind for me now these days is not galaxies, but rather climate change, is because of these things that I learned. So I looked around for an advisor, and I wanted to find someone, and this is someone who is also very familiar to Ruth. Don Webbles ended up being my PhD advisor. I wanted somebody who was doing practical work. I didn't want somebody who was doing the ivory tower. Come on in. I wanted somebody who was doing real world work. And he had just been working on ozone depleting substances and was turning to work on climate change. And so some of our first work was looking at the contribution of different gases, not just CO2, to reducing targets. Because as you know, carbon dioxide is, let me get rid of this so you don't have to see that there. Oops, there we go. Carbon dioxide is only one of multiple heat trapping gases. And if we look at the other gases like methane and nitrous oxide and the high GWP gases, we can get a lot more bang for our buck. And this was not just a popular topic back in the 1990s. This is a popular topic today, as you know, because, for example, we know that cutting methane today could get us a lot of emission reduction really, really quickly, like plugging oil and gas wells. So that's really at the top of the climate agenda today, and it's very timely and it's very relevant to decision making. Now, if you've been, I just want to take a brief detour here. If you've been tracking my photos, you might have noticed something else. All my mentors were men. I did not have any female mentors at the time. And so I'm really grateful for the fact that around that time, the Earth Science Women's Network started up. And I remember the first time they had a workshop at AGU, I went. And that was the first place that I saw other women, senior women, talking about what it was like to be a woman in science. back at a time when less than 10% of full professors in earth sciences were women, let alone women of color. So finding people, and now there's many more organizations. So there's 500 Women Scientists is another organization. There's organizations like Geo-Latinas. There's organizations like Black and Marine Science. Now, today, compared to before, there's so many more organizations where we can find ourselves, we can find connectivity. And one of my favorite organizations that I'm part of today is Science Moms. I'm not talking about my outreach yet, but this is just a slight tangent. And it's an organization to help mothers care about climate change. But we have a group of about 15 of us who are all women and climate scientists. And we all come together and sort of think through like, hey, how can we communicate better as mothers for the love of our children to help people understand why you care about climate change? And I just love it. I mean, look at Joelle in there. She's just got her hands full. She's an oceanographer. She's in Arizona. And she's like, what's the plan to solve climate change? So it's really important for people to see themselves in our work when we're communicating our work, as well as when we're bringing new people into our work. And then another thing, too, is I'm a Christian. And as people of faith, that's not something that we often see faith in these circles. But if you look at all the major religions in the world, they all have at their core stewardship or care over nature and loving and caring for other people. And so finding an organization for me that I could connect with that was also combining science with faith, which is what the American Scientific Affiliation is, was also really important to me and really helped in my trajectory in my career. But onward. So here we are. I had gone to grad school with Don Webbles. I was doing consulting because I wanted to do science that was relevant to real-world decision-making. And I got pulled into this report in the year 2003, Confronting Climate Change in the Great Lakes. I, being from Toronto, was part of the Great Lakes. So it was a group of ecologists. Everybody in the report was ecologists except for me and Don. And they wanted climate projections. And so I was like, sure, we can get you climate projections. And they're like, well, we want them for the Great Lakes. And so I made these maps using GRADS, if anybody remembers that program. And I was horrified by the scale of these projections. I mean, these people were looking at wetlands and a tiny little wiggle of Lake Superior on this map. And here we were giving them these, massive region-wide averages that meant almost nothing to them. And so for me, this was the second big inflection, or third if you count science as the first, inflection in my, not just my career, but in terms of what I was thinking about. I thought, I bet we could do better than this. People need this information. Ecologists need this information. How could we do better? And so I started thinking about, why do we need these projections? And I started writing about it, and I started working with the National Climate Assessment, and I started working with people in engineering and ecosystems and health and infrastructure and agriculture and all these different people across the spectrum to try to figure out, why do you need projections and how can we get you better ones? And so I started thinking about things, and I wrote an essay for ERL 6 years ago, where I literally said we're conducting an unprecedented experiment with our hope. We've never seen this much carbon going into the atmosphere this quickly. And planning for the future is based on the past, is like driving down the road looking in the rearview mirror. That's what we're doing. And it works great if the road's straight. I live in Texas. There's a lot of roads that actually look like this in Texas. You could drive down the road looking in the rearview mirror. But if the road looks like this, you can't. You have to look forward, and that's why we need projections. So I spent a number of years thinking about how to communicate this. And I sort of refined this metaphor. I took it to water planning conferences, and it was really sticky. I still hear from people today who are like, I remember 8 years ago, you told me that we were driving down a road looking in a rearview mirror. And so developing these metaphors to help this information stick in people's heads to understand why they needed it, that was what I spent a lot of time thinking about in the last 10 years. And then where we are today is a lot worse than we were 10 years ago. We know that our warming is unprecedented. This is the most recent IPCC report. And we know that it's not just about warming. We know that it's loading the weather dice against us. So this was another analogy I tried to work on, trying to explain to people how wherever you live, you have a chance of rolling a double six, normally, naturally, heat waves, droughts, floods. But as the world gets warmer, decade by decade, it's taking these numbers and it's turning them into sixes or even sevens. It's loading the dice against us. So people sort of had the idea in their head that it's global warming, right? And I'm like, no, this is actually global weirding. And they're like, oh, yes, that's exactly what's happening with the droughts and the heat waves and the wildfires and the storms. We're not saying they've never happened before. We're not saying that it's hotter everywhere, but we're saying that things are getting weirder. And so I tested that out all around Texas, where global warming is fighting words in many places. And people like the weirding. They're like, yes, that resonates with my experience. But then, going back to what I mentioned at the beginning, climate change is also an issue of justice, an issue of equity, and as the military calls it, a threat multiplier. And not to be too negative, but if we don't fix it, it will fix us. And we won't like that. So I was very struck by a quote by John Holdren a number of years ago. You know, he was President Obama's science advisor. And a number of years ago, he said, we have three choices: mitigation, adaptation, and suffering. We are going to do some of each. The question is just what the mix is. Because the more mitigation we do, the less adaptation is required and the less suffering there will be. And this quote really hit home so much that I actually designed entire presentations around this quote and went through, you know, what does mitigation look like? What does adaptation look like? What does suffering look like? And so for a long time, I was really thinking about how do we put together all the first two as much as possible to avoid as much as possible the last. And this was interesting to me because there's a word in there that up until then, up until he said this, I had never seen in scientific circles. Which word is that? It's an easy question. Suffering. Suffering, exactly. But today we see it in scientific circles. And we should, because that's what we're trying to prevent. And we know from, this is the climate action tracker. If you're not familiar with this, they have this really handy thermometer where they track all the countries' commitments to the Paris Agreement. And we know that we're not going to avoid suffering. We know that we're going to have to adapt currently to at least 2.7 degrees of warming. We still have the opportunity to bring this down. 2.7 is not written in stone, but we know that adaptation has to be part of this. And so that's where the projections come in, right? Projections are needed for adaptation. The greatest uncertainty is us. So then I started to think a lot about that. Well, what does that mean? If the greatest uncertainty is not cloud parameterizations, although those are uncertain, if the greatest uncertainty is not what's happening at the tails of the distribution, although that is certainly uncertain too, if the greatest uncertainty is not, you know, the structural uncertainties of not having the processes that cause the ice sheets to melt in the climate models, that's a big uncertainty. But if that's not the biggest one, if the biggest one is our decision making, what does that mean? Because we humans, in physical science, we don't study humans. We study the physical environment. The social sciences study humans. Yes. And so I, as a physical scientist coming from a physics background, I started to realize, oh, we need to be looking at a lot more than just the physical science here. Do you know the IPCC, the first report back in 1990, it was all physical scientists. All. And then the next report, they brought in the impacts. They started to get people who studied water and food and infrastructure. And then they got Working Group 3 going, and Working Group 3 is the technological solutions. So they do, you know, demand, they do the economic modeling, they look at the different technologies, they see, you know, what actions would reduce emissions by what amount. But there still is no Working Group 4. And what would Working Group 4 be? It would be, how do you get humans to take all this massive amount of information? If you piled up all the IPCC reports, they would actually reach the ceiling and probably pass it. And these are single space, like 10 font or 10-point font reports. So you've piled up all of these reports, but how do you get people to use the information to make good decisions? You're probably just sitting there laughing, right? Because you're like, yes, obviously.
Same question.
Yes. But this is something that we hadn't wrestled with as physical scientists, because we just assumed that if you just, you know, tell people the right information, they'll do the right thing, right? I mean, it's logical. Well, Plato wrestled with the same question, right? Plato had that whole rational man description. And what we've concluded since then is there is no perfect rational man. We are very irrational people. And so here we are doing the best science in the world with reports piled up to the ceiling, and nothing's happening. So what's going on? So that was very top of mind for me, is realizing that there's more to this than just the physical side, even training myself to understand that there's all kinds of different science, that what I had thought of as science was not the sum total of science. In fact, it was just a tiny fraction of it. So how do we show the impact of our choices really became a focus for me, because if we're looking at the future, we want to be using it to motivate people to change. And this may shock you today, but when I started doing future projections, everybody was using a mid-range scenario. That was just what they were doing, a mid-range scenario. So what does that communicate? It communicates, here's what's going to happen no matter what, right? Here's the scenario. Or sometimes they would use two mid-range scenarios, a slightly higher one and a slightly lower one. And so I started to ask colleagues, and it was a little bit uncomfortable because all these colleagues were older. You know, this was 20 years ago. And again, all the colleagues were usually male. And so I started to ask and to poke a little bit and to say, why are we using the mid-range scenarios? And so I remember with one project I was doing in the Caribbean, by then I'd already done a few projects where we didn't do that. And so, but when, you know, the senior scientist on the team was insisting, and so I really started poking. I was like, why? And he said, well, because the middle is the most likely. And I said, well, that's true for physical uncertainties. For physical uncertainties, they typically have a Gaussian distribution. But what are scenarios? What's the primary source of uncertainty in scenarios? Human choices. Since when are human choices Gaussian? Thank you. They aren't. Like, look at the stock market. Does that look Gaussian to you? Look at any human decisions. They are not Gaussian in the remotest. And so I was pushing and pushing the scientist, and finally, you know, trying to refuting each point, and finally he said, well, one time I was on an advisory panel for an economic organization, and that was his be all and end all. That was why we're using the mid-range scenarios. And I was just like, oh my goodness. So I started to realize that not only is it really important that we adequately represent extremes, obviously we know that because that's what causes the biggest damages, but it's really important to show a range of projections and to translate that into global temperature thresholds, because that's what the Paris Agreement is in. The Paris Agreement isn't you know, a RCP scenario or an SAP scenario. The Paris Agreement is 1.5 degrees. So I started working on translating climate projections into weather stations. And I started translating it not just into daily temperature, but into the average temperature on the hottest day of the year. So you could identify your weather station and be like, oh my gosh, the hottest temperature on our, you know, at our weather station is going to be 130 degrees by the middle of the century if we don't do something about this. And that's very different than saying global temperature will increase by 2 degrees Celsius. How are we translating here? We're translating in terms of the units, Fahrenheit versus Celsius. We're translating in terms of the geography, my city versus the world. And we're translating also in terms of the metric, not average temperature, but hottest day of the year, which is something that sticks in people's minds. It's sticky again, like the rear view mirror, like the global warming, like the loading the weather dice. So the very first time I had the opportunity to do this was in California in 2003, right after the Great Lakes. I gave everybody a piece of my mind in the Great Lakes assessment, and, you know, be careful what you wish for, right? Because they're like, oh, so you want to do a higher and a lower scenario, do you? Well, here, let's do it for California. And so I was like, well, great, because psychologically, when you do the higher scenario, you're showing what we can avoid. And when you're doing the lower scenario, you're showing what we have to adapt to. And I was working with the Union of Concerned Scientists, who is just up the street in Brattle Square, if you don't know, and they're a great organization. And we were showing the outcome for California for air quality, water supply, wine grapes, agricultural production, air pollution, human health, wildfires, what a higher versus lower scenario would look like. But here's the problem. Only one climate model in the world had run the highest scenario, which at that time was A1FI, for anybody who remembers the SRS scenarios. Why? Because when you talk to the physical scientists, they're like, oh, that's not likely. Well, on what basis did they decide it wasn't likely? Guess what? It turns out we tracked A1FI for 20 years religiously. Year by year, we just wouldn't rate up A1FI. But nobody ran it because they decided it was too high. They weren't economists, they weren't social scientists, but they just sort of decided it's too high, so they didn't run it. So we only had one model to work with, and that's not enough. So I had to go cap in hand to 2 other models. I chose the US models because I figured they might be open to it, and beg them to run A1FI, and they never had before. And they did, which was awesome. So we ended up with 3 models, and we did this for California. And we looked at the impact of a higher versus a lower scenario on the water supply, the snowpack, the health, the ag production. And it was so impactful that when the governor signed the first greenhouse gas emission target of any state in the country in 2005, our paper came out in 2004, he had our entire California author team standing in a semicircle behind him, including Steve Schneider. What goes around comes around, which is very cool. And they quoted our California study in the executive order. That was the power of showing that our choices matter. Isn't that crazy? Because they felt like they could do something about it. If we just showed a middle range scenario, then what could they do? Then why have an executive order, right? So that was what I spent a lot of time thinking about, and I still do. But then once the Paris Agreement was signed, I was like, who knows what RCP is? Okay, let's be honest here. Who here in this room knows what RCP stands for? I'm not judging you. Okay. Higher, please. Okay. So here we are, and I think about a third of us know. Now, you had your hand up. I'm going to call on you. What does it stand for? Yes.
Ordinal.
Sorry?
Ordinal.
Ordinal. And what does RCP stand for?
Something pathway.
Yes. It does. Representative concentration pathways. You see that? We work with these things all the time. And in case you're wondering, SSP now stands for Shared Socioeconomic Pathway. But we work with these, I'm sorry, but thank you, you're a good sport. We work with these things all the time, and this is the most useless naming convention in the world, right? But on the other hand, with the Paris Agreement, most people know 1.5 or 2 degrees because most of the world operates in Celsius. I'm Canadian, so I include myself in that. So then I started to think about, well, shouldn't we just be talking about what's going to happen when we reach 1.5 degrees? Like, how many days over 100 degrees are you going to have in Boston when it gets to 1.5 degrees or 2 degrees? And so we did a study on corn in Iowa. And we looked at what happens if the world gets 1.5, 2 degrees, or 3 degrees, and what happens to corn yield in Iowa. And we worked with farmers and producers, and we showed them the results, and they told us that they could adapt to 1.5 degrees. 2 degrees would be expensive. They could keep operating, but they would be losing out. And then 3 degrees they couldn't adapt to. Well, all of a sudden, we had a group of corn farmers in Iowa who had a position on the Paris Agreement. That's the power of translating it. So then people said, but how do you take global climate models and translate the outputs? And I was like, just do this. Just plot the global mean surface temperature anomaly against time and take the 20-year period for each simulation when it passes that threshold. And then just cut and slice and dice those 20-year periods and put them together. So I pushed again, and I actually got this into my chapter of the National Climate Assessment last time. And I've applied it to papers because instead of having scenario number 1, scenario number 2, and scenario number 3 for a short time period, a near term, a mid-century, and end-of-century time period, no need for the detail. My point is just how many maps you need to show this information. Instead of having 3 different scenarios for 3 different time periods, all you have is +1 degree, +2 degrees, +3 degrees, +4 degrees. Here's what it looks like. You pick. Where do you want to end up on in here? Well, that gives you a position on the Paris Agreement. This is so fun. I've never gone through and just sort of like shared my thought processes before. I'm really enjoying myself. I hope it's not too boring for you too. So then I started to apply this, and I worked with Washington, D.C., with Chicago, with Houston. I worked right here in Boston and Cambridge. We did projections showing what would happen with average annual temperature, days above 90 degrees, days above 100 degrees right here in Boston. I worked with the Union of Concerned Scientists to turn this into really pretty figures. We looked at this. This is a calendar. So this isn't a scientific figure, is it? But this is showing the summer calendar. So what do we have here? We have June, July, and August. And what it's showing is how many days you'd have over 90 degrees and how many days you have over 100 degrees compared to the baseline. So this is your whole summer. And all of a sudden, your whole summer is full of orange days. So that sends a different message, right, than just a bar on a bar chart. So I still do a lot of this. In fact, 2 years ago, I wrote a book with my colleague Rao at Argonne. You see some other familiar names there, including Don Lovels. We wrote a book on how do you generate and use high-resolution climate projections. It was published by Cambridge University Press. And if you don't know much about the topic but you want to, I highly recommend it. And then for the last 5 years, I've been working on something that I call the Sagrada Familia. Why? Anybody here been to Barcelona? Seen the Sagrada Familia? Yes, a few people have. It is very unique. It is out of the box, and it's never finished. That's the main reason, but the other two are true. But now I'm really happy that we finally actually have a preprint it. We finally submitted something that I've been working on for 5 years, which is a statistical method to turn global model simulations into ultra-high resolution projections that you can apply to any observational data set, including satellite data, weather stations, reanalysis, quasi-observational, gridded data sets, anywhere in the world. And we've tested it very thoroughly, and it is accurate out to the 99.9th quantile of the distribution of temperature and precipitation. And we've actually done some tests showing that you can't get anything more out of the global model. You have to go dynamical, which is very important, but also a lot more expensive. You have to go dynamical if you want to get any more information than what we've been able to do here. So I'm really excited. We submitted it to Earth's Future. It's already posted, although it's in review. And just to give you one example, over here, a previous method that I used for all the city work I did was an asynchronous regional regression model. That's what ARM stands for. It's a parametric quantile mapping method. And as you can see, it had some significant biases. And what we're showing here is the Indian subcontinent. So what we're showing is maximum temperature. And as you can see, once you get out to the really high temperatures at the bottom, that's the 99.9th quantile. So that's the hottest day in 1,000 days. So that's pretty hot, right? Like hottest day in 2.5 years. As you can see, there's some really big biases along the coastline and in the mountains. And so we dug into it, and it turns out that those biases in high temperature result from only 1 month. Hydrologists, any guess which month that is and why? Turns out the reason is hydrological. High temperature biases at very high elevations in the Himalayas in 1 month of the year. Why is that? I know, Eric did not warn you there'd be pop quizzes.
We have an expert on the Indian monsoon here.
Any guesses?
June,
And why would that be?
because it's a interface between when the monsoon starts and monsoon and the pre-monsoon, the summer season.
Mm-hmm.
I guess.
Yes, that. Okay, very, very close. I think that's probably, my guess would be that that's probably the secondary modifier on the bias. But what we found is, I'll give you another clue. We found a similar bias, but not as large, in the Rocky Mountains in April, and in the Andes Mountains in October. Snow melt. Yes. Really? Yes, it was. Cool. So what was happening was the shift in snow melt was making the statistical relationships non-stationary. But the monsoon modifier is a really interesting one. We'll have to talk more about that. Because with precipitation, we also see biases, obviously, in precipitation. So we're still, because this is the Sagrada Familia, it's always going to be improved. And so the next thing we're introducing is a phase shift. So in places where we see that, for example, monsoon seasonality is shifting or snowmelt is shifting, if you introduce a phase shift into the statistical relationships, you can capture that too. So this is obviously top of my mind because it just got submitted. And where we are right now is, like I said, this is super flexible. So you can apply this code, it's MATLAB code. It uses a signal processing approach where we decompose the signal into multiple timescales, and you can apply it to any data set. So the code is going to be on GitHub so that people can just download it and use it. So far, we're applying it to gridded data, station data. We're going global next, and then we're doing derivation of secondary indicators by global temperature threshold. So 100 degrees days, at 1.5 degrees of warming or 2 degrees of warming around the whole world, what does that look like? But I forgot one big thing that I think about a lot. So going all the way back to here, when this report came out, and this was 20 years ago, we showed up, all the authors showed up for our final meeting, and they brought in a media trainer. I'm like, a media trainer? Why do we need a media trainer? You just tell people the facts and they'll do the right thing. Well, turns out not so much, right? And that was where I learned that communication is a science. People study it. There's techniques. There's ways to do it well and there's ways to do it poorly. And sadly, in science, we often do it poorly. I was shocked. So that was where I realized that it's not only about doing the best science in the world, you also have to communicate it. And if you don't communicate it, people aren't going to use it. So that was where I started to communicate. And I moved to Texas around the same time because they wanted my husband, not me. I was a +1. Yeah, I'm serious. He was an endowed professor at Notre Dame at age 27. He's hot stuff in the applied linguistics world. They had to put up with a climate scientist in West Texas to get him. The joke is he got bored and left. So now he runs a nonprofit and he's very successful outside the academic sphere and he's still stuck with me. And so that's where I started doing a lot of my communication. I started doing my YouTube series. I started doing a lot of my media. I started doing a lot of my social media. I started studying what Yale is doing. I started studying what effective communication looks like. I started being a guinea pig, other people studying me to see what I was doing. And then I eventually wrote my book, Saving Us. And I wrote this the same year. Oops, I can't move this down because look at me. Shoot. I wrote this the same year as I wrote the downscaling book. But this book has one chapter on the physical science, and the rest of it is all social science and stories. Because when we tell stories, our brainwaves align, and people enter into and empathize much more with what you're talking about. So what's top of mind with me today is thinking about how can we more effectively communicate what's in our heads by connecting it to people's hearts, and then, even more importantly today than ever, connecting people's hearts to their hands. What can they do to make a difference? And that was exactly what you said too, right? You were talking about solutions. So I know we're nearing our end, and if anybody has to run out the door, feel free, because I know you might have to be bolting across campus. But I'm going to go back to where we left off at the top here and see what you had to share. I know that's not true. Okay, strange. There was something in there, wasn't there? There we go.
Responses.
Okay, thank you. Okay. All right. Does the technical work being done? Yes. So I was just at Climate Week, and the gap between work in the lab versus being implemented in the real world is shrinking faster than I've ever seen it before. People are like literally, banging down doors or moving to tech companies. I met a climate scientist who's using AI to reproduce convective permitting models, which, as you know, those are highly computationally expensive. He can reproduce most of the convection permitting regional climate model using AI at a fraction of the cost, and he just left Columbia University to go to NVIDIA. So there is a huge crossover like I've never seen before. My postdoc left and went to a private company where they're putting climate projections into planning for companies. I was talking to the United Nations, and I was talking to Microsoft, and I was talking to Google about how to be using AI to synthesize scientific data and getting it out in the public sphere faster. So 20 years ago, I might have said I'm not sure. Today, 100% yes, 100%. The second one's really interesting. So the Nature Conservancy, who I serve as chief scientist, did a study this year where they found that 78% of the land that solar was being built on in India was valuable ag land. And then, did you know the #1 cause of deforestation in the state of Virginia? Solar. Yeah. So this is a big issue. And so one thing that the Nature Conservancy has done is they've created this tool called SiteRight. And they've got it so far covering the United States, Europe, and India. And it maps out all of the migrating birds, bats, endangered species, unique ecosystems, agricultural land, unique watersheds. And it also has solar potential and wind potential, so it shows you where to put these things. So this is something we need to think about, because if we go too far with a solution without thinking about the repercussions, we could end up in just as big a problem as we had today. So it's really interesting because I've been collecting questions using Poll Everywhere for about 10 years now. And typically when I give a public presentation, I say, just ask a question, any question, not this question. I just, people can put whatever they want in. Top question every time. I could be talking to scientists, doctors, architects, community members, Catholic nuns. I've got the same question every time. Is it too late? Can we still be optimistic? Is there hope? Are we screwed? Same question, essentially, every time. So that's why I wrote Saving Us. And it depends on how you define optimistic. If you define optimistic as everything's going to be fine, the answer is it won't be unless we do everything we can. But if you define that as, if we do something, will it make a difference? The answer is yes. 100% yes. In fact, the IPCC 1.5 degree report concluded every action matters, every bit of warming matters. So I define hope as it starts in a bad place. Because why do you need hope if everything's fine? You don't, right? You don't need to be optimistic if everything's fine. So you're starting off in a bad place. You know a better future is possible if you do everything you can. You have to lay out a path from A to B, and you have to figure out what you can do yourself to help move people on that path. And that, I believe, is where hope comes from. So that's probably a good note to end on, but let's do 2 more. Do we have time? Okay, we do. We have 2 minutes. We can do this. The greatest challenges in climate science right now, well, I've reviewed some of those already. I feel like connecting the head to the heart to the hands is really tough. We have so much in our head. Like if you pictured climate change as a body, our head would be so gigantic, it would be like falling over sideways. And we really have to build out the heart and the hands, which is why do people care and what can we do to make a difference? So that's a big challenge, is just making sure that the science doesn't dominate the headlines. Like they did a study of the BBC's climate reporting. And up to a few years ago, almost every BBC story about climate change had one of 2 photographs, a polar bear or an iceberg. Now, unless you're a polar bear living on an iceberg, that's not connecting to your heart. So we have been very climate science heavy, very head heavy. We have to figure out how to translate what we do into something that matters to people and can motivate change. But in terms of the other greatest challenges is, we don't know what we don't know. We have never pushed the planet this far, this fast. 55 million years ago, there was 1/10 the carbon going into the atmosphere as we're putting in today. So the unknown unknowns and the known unknowns are what keep us up at night. And I think those are the greatest challenges, is really trying to figure out how will this experiment unfold. How do you not get overwhelmed is actually the perfect question of all of that. So I've discovered that hope is not going to find you. Hope does not motivate positive, news stories or even positive peer-reviewed journal articles. But if you practice hope, if you go out and you look for hopeful information, it can find you. So I started to practice it. I started to go out and look for helpful information. I find it on social media, actually. That's where I find a lot of helpful information. And I started to collect it, and I started to share it. And then other people said, well, how can I find it? And I was like, well, I guess I could start a newsletter. So I started a newsletter a year ago called Talking Climate. And I just sort of threw it out there. And now I've got 80,000 subscribers. And every week I share good news. And it's color-coded green. And then I share some not-so-good news, color-coded red, because we need to know what's happening. But I color-code it red because some people want to skip it. In fact, some people have been like, could you just have a pop-down menu? I was like, no, MailChimp doesn't allow you to do that. Maybe somebody here could figure that out, but I don't have time. And then I have something in blue, what you can do to make a difference. And so how do I not get overwhelmed? I do get overwhelmed sometimes. And I don't think I'd be human if I didn't. How can we not be overwhelmed? With all the work, with all the data, with all the stress, with all the worry and anxiety. But I don't get permanently overwhelmed because I actively practice hope by going out and looking for what people are already doing and recognizing that when we look for solutions, they're all around us. And by recognizing also that every single one of us has a role to play. Thank you.
Thank you so much, Katharine. So we can open up the floor now. I noticed one or two of the undergraduate students, they had to leave because of classes and such. But I was going to say, let's reverse a little bit based on what you said and what we know is that is the next generation. Mm-hmm. We had some high school students also, but only in the summer, not right now. But if there's an undergrad student, I'd like, please, and, I'd like you to introduce yourself and say what you feel about this.
Mm-hmm. I can start.
Diane left, sorry. Diane had to leave for a class.
Record. I think we could probably turn the recording off.
Okay.
So it's just harder to follow. Yeah.
I'm Anika. I study computer science and environmental